Okay.
Wait. See here you have to start
Streaming.
same place.
Okay. Okay.
Same place you have to stop.
Okay. Hello. Hello. Yeah. Welcome everybody to the live session of convective heat transfer. So I hope you guys are doing well in terms of homework and following the course content. So if you have any questions, we would welcome it at this particular point. Okay. And so so I guess we had a few questions which were already there. So you might want to state your name.
So D. Anand Kumar is a student. He's telling, okay, D. Anand Kumar is a student. He's saying nice teaching.
Anant Kumar, thank you for the nice compliments. Appreciate it. Hope you are also liking the course.
Krishnamurthy, who's a faculty, he says that, respected sir, the content of the course is most important in the field of fluid flow also in convective heat transfer. For this subject, we need to refer to any one good book for better understanding. So can we able to get convection heat transfer fourth edition by Adrian Bejan textbook soft copy, since this textbook is very costly, which I am unable to afford. Please kindly accept my request and do the needful.
Dr. Krishnamurthy, thank you for your comment, but the problem is that these books are all copyrighted. As a result of that, the soft copy is also something that one has to buy. Okay, so there is no mechanism by which I can give you a soft copy of the course, soft copy of the book. But what can happen though, however, is Mr. Krishnamurthy, what can happen is that there are Indian editions of these books which are available, which I think is much less costly than the international edition. So I think you can buy some of that. I think hope this answers your question.
Akash Chakole, who is a student, asks which types of application has of convective heat transfer.
So Akash, okay, convective heat transfer is there everywhere. Like for example, right from your solar energy application to your gas turbines to the coffee that you drink at home, or the cloths that you actually dry in your washing machine. Everything is convective heat transfer, right? So convective heat transfer is the mode of heat transfer apart from radiation, which you basically see everywhere and in all applications, because it builds on the Navier-Stokes equation, because Navier-Stokes equation is the momentum balance. Now, convective heat transfer needs you to solve one more set of equation, which is basically the energy equation. So it basically tells you wherever there is fluid flow and wherever there is an energy differential, or it is basically a temperature differential, you are going to have convective heat transfer issues. So it is there everywhere, okay, and it is there in many applications. Thank you. So I guess we wait. So read out the question. Can we mute the mic once? Oh, audio. Hello, Akash. Hello. Yeah. So,
Akash Kumar asks, sir, what is meant by advection?
so if you just think about it like this, okay. So, advection is meant when that particular parcel of energy, okay, is carried by the flow field. So in this particular case, when actually energy is carried by the flow field, actually it can be energy, it can be momentum, it can be anything, right? So the idea over here is that you have energy that is transported, that is riding on the velocity field, basically. So if you look at the, for example, the energy equation, okay, that means after you must have seen the Navier-Stokes equation already. So if you look at the energy equation, right, you will see that in that particular energy equation, there are terms like u dt dy and u dt dx and v dt dy. So that essentially means that your thermal energy is being transported by the velocity field, and that is in common parlance is called advection, right?
So the next question is by Veda Vyasa. If there is a plate of length, say 25 centimeter, how the velocity and temperature profile are measured within the boundary layer?
Okay, so the length of the plate effectively has nothing to do with it per se, okay, except for the fact that if you want to know the thickness of the temperature and the velocity boundary layer, then the length of the plate becomes important. But if you are talking about the general length of the plate at any point along the length of the plate, okay, you can calculate and you can write the velocity profile as well as the temperature profile. You already know about the Blasius solution, and the temperature profile also has been covered to a certain extent. Okay, so if you are talking about measurement, on the other hand, right, if you're not talking about a theoretical basis, if you're talking about measurements, then there are multiple ways in which you can achieve this. For example, the temperature can be simply measured by putting in a bunch of thermocouples. If your thermocouple bead size is sufficiently small, you should be able to measure it within the boundary layer. Okay. On the other hand, if you are going to look for more sophisticated measurements, then you have to go for laser-based diagnostic techniques, which are a little bit out of the league of this particular course. Similarly, for the velocity, there are ways to measure the velocity. For example, there is a technique called hot wire anemometry, by which you can measure the velocity within the boundary layer. And at the same time, you can use field measurement techniques, like, for example, particle limit velocimetry, in which you can measure the velocity within the boundary layer. So there are multiple ways in which this can be done. Okay.
So the next question is from Prabhakar Bhandari.
Okay.
He's a faculty. NF equation is one of the $7 million problems. Can you explain, sir, how it is a $1 million problem and why its analytical solution is not possible?
Okay, so the question that you have asked is more into the mathematics domain, right? And Navier-Stokes equation is basically the $1 million problem is about the smoothness of the Navier-Stokes equation. Now, but though it is not completely related to the content of this course, I will try to give a generalized answer to it. The basic problem with the Navier-Stokes equation is not the equation per se. The equation is a well-known equation, and there are not really any unknowns. It's a very well-posed problem, actually, the Navier-Stokes equation. But the problem with the Navier-Stokes equation is that it's a multi-degree of freedom system, and it's highly chaotic in nature. That's why when you actually use Navier-Stokes equation for solving your turbulent flows or any other similar such flows, okay, you cannot actually predict what will happen. There is no analytical solution because of the nonlinearity of the advection term. So in order to say that where the bifurcations are going to happen, how the bifurcations are going to happen, and in order to predict what will happen to the Navier-Stokes, how the Navier-Stokes equation are going to behave for any particular flow situation, okay, there is no predictive methodology unless you do a complete CFD, which is very costly, or you do a bunch of measurements, which does not give you any predictive capability as such. As such, it remains a problem which is still open. So nobody has got a solution to the generalized Navier-Stokes equation. And that is where it is a $1 million problem. Thank you. Next.
The next question is from Shushwant Lingareddy. Sorry about that. why the Nusselt number is higher in uniform heat flux case compared to the uniform wall temperature case for a particular cross section?
Yeah, so you can see this very clearly, right? If you plot the profiles of the temperature of the wall and the temperature of the flow, if you recall that in one case, okay, because you are maintaining the wall at a constant temperature versus you are supplying a specific amount of heat, if you recall the temperature profiles in those cases, one was parallel to each other, maintaining a constant slope, right? And in the other case, you had the temperature which was kind of showing an exponential profile, right? Especially in the case of a uniform wall temperature case, where the temperature actually grew, and so the margin, that means the delta T, slowly and steadily shrunk. So this would give you the answer that why the Nusselt number is higher in the case of uniform heat flux. Thank you. Okay, that's the question.
So Ved Vyasa again asks, in case of natural convection problem, I want to calculate the temperature of a plate which is kept in atmosphere, and I want to use G as 9.81 for a given Rayleigh number. How to calculate the temperature?
I guess tempera means temperature. Okay.
In case of
In the case of a natural convection problem.
so Rayleigh number is given, so G is given, so we have to calculate the delta T.
So it is, you just use the formula of the Rayleigh number, I guess. That's the only thing. That you know the Rayleigh number formula, you need to know the relevant length scale here, which is, I guess, it will be the length of the plate, right? Or it will be the length of the plate, and the beta, you need to know the fluid properties, which is beta. And you can use G, and so you can calculate what will be the delta T. You won't be able to, then you need to know one more temperature, either the plate temperature, you need to know to calculate temperature of the flow from delta T, essentially. So you can use any, now the Rayleigh number is pretty standard, you already have it over there, so you can just use that definition.
Initially, I don't know the properties, he says. So for
Okay.
you need to have the kinematic viscosity square also.
Yes. Yeah, I guess, okay, we read your comment just now. Okay, so if you don't know the properties, then you cannot. Okay, you need to know the properties of the fluid. Okay, so if you do not know the properties of the fluid, then you cannot calculate it like that. Okay, next question.
Next question is from Shushwant Linga Reddy. He says, we always talk about the phenomena happening after the entrance length and do its analysis. Why are we avoiding the phenomena happening before the entrance length?
Yeah, so we are not avoiding anything at this particular point. The point is that for pedagogy purpose, okay, you need a well-behaved flow that is entering. Of course, you are right that real-life flows are seldom has that very nice profile that is the uniform profile at the entrance, right? So, but if the profile is a little bit convoluted at the entrance, that means the profile is not a top hat profile like what you see. Okay, then of course what will happen is that your flow physics actually becomes much more complicated, because then your u will be a function of now y, right? And then you have to put this value in, or put this profile in, and then solve your Navier-Stokes equation again, which makes it a little bit more cumbersome for a pedagogy purpose. But obviously you can solve it. There is no problem with it. And people solve it all the time. So you can solve it analytically, perhaps not all the time, but you can definitely solve it computationally or even experimentally. Okay, I think Veda Vyasa has another question.
So Veda Vyasa, in response to the previous question, he says that fluid properties depends on the film temperature. So of course, so is the 1/3 law.
Yeah. But he doesn't know the temperature. I guess that is the question.
Yes.
So you have a catch-22 kind of a problem that you don't know the temperature. But if the temperature setting is not all that, so what you can do, perhaps you can do something like an iterative kind of a solution. You may assume that whatever is the room temperature, then calculate whatever is the Rayleigh number going to be, and then calculate the first order estimate of the temperature. Then you can use that temperature setting to recalculate your property, so to say, using a typical 1/3 law, like T1 and T2 by 3, something like that. And then you can recalculate the Rayleigh number and then come with an estimate of the temperature. But all these things are literally, I mean, if you are dealing with buoyancy-driven flow, you are essentially assuming that your delta T is not that high. The Boussinesq's approximation is actually valid for that. So essentially, I don't see the property will change by that much. But if you have a situation like that, then the situation is a bit more complicated. Thank you.
One more question is asked by Akash Kumar. Sir, in advection, the mode of heat transfer, only convection or both conduction plus convection?
You know that if you look at the energy equation, your conduction term is basically nothing but your the conduction term basically comes on the right hand side of the equation, right? So if you take a convective heat transfer equation, what you have essentially is basically you write the full equation. Out of that, only the right hand side okay, which is basically your diffusion term essentially. That is your conduction term, okay. And the temperature changes, and if you take on the left-hand side, and if it's a transient heat conduction problem, you don't consider there is any velocity gradient. So you just consider the temperature change with respect to time. So you just put the velocities equal to 0, you will recover the conduction equation from the convective heat flow, from the advection equation essentially. Okay.
The next comment is by Vedvyasa. In CFD software, assuming that two temperatures are known, they recalculate the value of G using given Rayleigh number. To what extent the answers are correct?
To what extent the answers are correct? Okay, assuming the two temperatures are known, they calculate the value of G using the G. Why would you calculate G? I didn't get that part.
Either fluid properties can be calculated.
I mean, G is G unless you are doing your things somewhere else. I would say G is G, right? So why would you recalculate G? Are you trying to do it as a validation exercise or something? So I mean to say, what I mean to say is that if the Rayleigh number is given, then obviously you have calculated the temperature difference and using G and stuff like that, right? So there is nothing, I mean, what you mean by the answers are correct, that part I'm not getting. If you can clarify your question a little bit or articulate it a little better, then that would be nice.
Who is
You
the
can
person?
mention Rajalingam.
Rajendra.
You can mention these questions came from Google.
Okay.
Okay. Okay.
Okay.
We
So
take that question. This is
okay. So the next question, I think Ved Vyasa is clarifying the previous question. I will clarify the question. Assume that the two temperature of plate is buoyancy driven flow are known in cavity. They recalculate the value of acceleration due to gravity to match given Rayleigh number. This is generally done in CFD softwares. By this method, to what extent the contours of temperature are correct?
okay. I assume that in a buoyancy-driven flow, they recalculate the acceleration to match the given Rayleigh number. So I'm not generally aware of what is done in the CFD software, so I cannot really comment. But I guess what you are talking about, that if there is any error in calculating the temperature profile, it will give rise to a wrong value of G, and they try to reiterate and try to kind of come up with a match with the value of G that you normally get. I guess that's what you are talking about. So yes, I mean CFD softwares might have that issue, that the temperature may be not calculated properly due to multiple reasons, numerical error, mesh problem, and stuff like that. But I'm really not aware that how the CFD softwares that you are talking about actually operate. So, but I guess what you are talking about is a validation of the question, a validation of G, and then somehow converge to the right temperature. Thank you.
So the next question is from Rajalingam. He's a faculty. The first question is, Sir, I am designing a transparent insulated water bottle of 1 liter. For better effective time, what major factors should I kept in mind for better effectiveness?
Okay, I don't know what you mean by effectiveness. I guess what you are trying to do is that you are trying to keep your water temperature to be the same, right, over a period of time. So I guess you are developing some kind of a thermoflux, right? I guess that's what it is. So in this particular case, you have to take care of the insulation. So you write the problem like this: there is water inside a cavity, right, or a bottle. You can consider it to be a chamber, and this cavity has a certain wall thickness, and outside the cavity it is atmosphere, right? So generally what will happen, that heat will, if the water is hot, the heat will go out. If the water is cold, then it will be heated up to the normal room temperature. So you need to put a sufficient layer of insulation so that you can maintain that temperature gradient across the atmosphere and the water within the bottle. So you have to take care of your insulation thickness. So if you consult any book, okay, you will find that how to calculate the insulation thickness. But in this case, the convective heat transfer outside the bottle, you have to assume a value of H. So that H depends on what environment you are in, right? So that can be as low as 10 to as high as whatever, if there is a forced convection going on outside. Okay, so I guess your answer to your question lies that it depends on your boundary conditions, obviously. It depends on your boundary, what kind of a flow that you are dealing with, and accordingly you can make your insulation. And the second question?
So the second question is from Rajalingam, who is a student. Sir, your course is very knowledgeable. When calculating convective heat transfer coefficient H, we didn't consider the properties of solid material like thermal conductivity, etc. The different material with same surface roughness can produce a similar heat transfer coefficient. I'm assuming that is the question.
Yeah, I guess. So, it is not necessarily true that surface roughness cannot produce anything. Okay, so surface roughness can produce local, what we call vortices and stuff like that, which actually can augment your heat transfer coefficient. So, but if the roughness, what you are, I think, talking about is the roughness is so low or something like that, that it doesn't affect the heat transfer coefficient. It depends on your assumption, what you are trying to do. But in general, surface roughness can affect your heat transfer coefficient. And I think the other question is that H was calculated based on, without taking into account the solid material, but it is actually the roughness and the contouring which basically is of more concern over here. So if you can consider it to be the roughness like a wavy channel, for example, you will have a lot of arrested stagnant flow. which will change your heat transfer coefficient completely. Okay, so but it is a more complicated problem. Okay. So students, before we close the live session, I just wanted to mention a few things about the convective transfer course in general. Okay. There is one more question which I will take just after
So
this.
Prabhakar Bhandari, who is a faculty, he says, "Sir, can you elaborate why heat transfer is miniature channel is more than that of conventional channel?"
You mean to say macro channels, I guess, what you are talking about. Okay. Heat transfer in miniature channel is more than macro channel. Well, that is not completely true always. Okay. I don't know exactly. Are you talking about a specific application, or what do you? I mean, what do you specifically have in mind? Uh, Okay, we will take up this question a little later. What I wanted to say in general to the general audience is basically, when you do a course like convective heat transfer, actually pay a little bit of attention to the fundamentals, because everything that you do is kind of, comes from a fundamental understanding of why heat and mass transfer is important and how it is linked with the fluid flow. So what you need to do over here is basically, you know, uh, develop a very strong sense of physical intuition about the problem. Like, for example, what is a boundary layer, what is meant by the boundary layer. In a natural convection, what is natural convection, how the flow actually behaves the way it does, what are the different regimes in natural convection. So instead of basically, trying to learn things by heart, I think it is more prudent if you can maintain a little bit of, a fundamental understanding, because you may forget the other stuff. You may even forget some definitions, but I think your physical insight should remain. So I guess the last question of this series is microchannel versus conventional channel. Okay, so I guess if you are talking about from in a microchannel, normally the Reynolds number will be rather low. So I don't know why you think that the heat transfer will be more so than in a conventional channel. Uh, so but in any case, I think where you are coming from is maybe because the boundary layer thickness is rather short or rather small, and as you know that most of the heat transfer happens is basically related to the boundary layer thickness. Your H is dependent on 1 over delta. So basically, once the delta is small, your heat transfer coefficient will be rather high. I think that's where you are basically coming from this particular form. I think that's the only reason that I can think of on the top of my head at this particular point. Okay. So I guess we can close the session for now. Okay. If you have any other questions, feel free to write it in the forums and in the Google form, right? Okay, and feel free to ask me or the teaching assistants. Okay, they should be able to answer your questions, and if you can write also emails to me, I will try to respond to those emails as early as I can. Okay, so have a nice time, and I guess prepare for your exams.